All right, let's get started here. So, picking up from the last class, um, you remember we were talking about the Ising model without interactions. Okay, and um, in the last class, I got as far as figuring out what's the entropy for the collection of states with a particular value of the magnetic order parameter M. Um, and I also figured out what's the energy of interaction with the magnetic field. Okay, so there's no interaction of one spin with another yet, but there's some interaction with the magnetic field. Okay, so this then makes the total free energy that we worked out. Okay, and so this is the free energy, and it's divided by kT. As I mentioned last time, I think I forgot to say it's also divided by n, the number of spins in the system. Okay, so this is a plot of what that free energy looks like as a function of m. And now I can adjust my little slider and see what happens to the plot as I change the magnetic field. Okay? And so you can see the important change is that when there's a positive magnetic field, the minimum shifts, right? The minimum is no longer right at zero. It shifts over to a positive order parameter. And when the magnetic field is negative, then the minimum shifts over to a negative order parameter. So we might say the magnetic field induces an order parameter, right? There's some induced magnetization, which is a result of the magnetic field. Okay. Now, we might want to know how big is the induced magnetization as a function of magnetic field, in order to make a prediction that we could give to somebody in the lab. Okay, so one thing I could do would be to look at a graph like this and see where's the minimum. Okay, so I can see when the magnetic field divided by kT is negative 0.81, the minimum here is about magnetic order parameter of negative 0.7. Okay? So I can write that down in a notebook, right? And then I can change the magnetic field to some other number and say, well, what's the next magnetic order parameter, right? So I could write down a whole bunch of things in a notebook and then make a plot from that. In this case, I can do a little better than that, right? I can actually find where's the minimum by doing a little bit of calculus, okay? And so this is the plain old calculus like you learned in a first year calculus course. If I want to know where is the minimum of a plot like this, I can calculate the first derivative and set the first derivative equal to 0 and solve for the magnetic order parameter. Okay, so let's do that just for practice. Okay, so I'm going to stop sharing the graph and I will start sharing my whiteboard. And let's see, you see this iPad now, right? Okay, good. So if I start this calculation, all right, I would say, let's remember the form of the free energy that we had, that the free energy is minus H and M, right? And then plus KT N times this combination, 1 plus M over 2 log 1 plus M over 2 plus 1 minus m over 2 log 1 minus m over 2. Okay, so you remember this is what we figured out in the last class, right? Okay, looks sort of familiar. Good, so if I want to know where's the minimum, okay, so find the minimum. Okay, so we want to take the derivative with respect to m and set that equal to 0. Okay, so I don't always want to do a lot of algebra in class, but I'll do it for once right now. Okay, so let's see. If I want to take the derivative of that free energy for the first term, that's minus hn. Okay, and for the second term, ktn. And let's see, I have the product, right, of two functions, right, this times this. And so I have to use the product rule, right? And so the derivative there is the first thing, 1 plus m over 2 times the derivative of the second thing. So that's 1 over 1 plus m, okay? And then I add the derivative of the first thing, 1/2, times the second, which is log of 1 plus m over 2. Okay? And then likewise for this next set of terms, again, it's time to use the product rule. So it's the first, whoops, 1 minus m over 2 times the derivative 1 over 1 minus m, minus, and then plus the derivative of the first, which is negative 1/2 times the second, log 1 minus m over 2, all like that, right? So this stuff all has to equal 0, right? And hopefully I'm doing the calculus right and I'm not going to embarrass myself, but you never know. So let's see, in this, we can cancel the 1 plus m's and we get 1/2. And here we cancel the 1 minus m's and we get negative 1/2. So this whole thing cancels this whole thing. Okay? And so what's left is minus hn plus ktn times what? Times 1/2 of the difference of those logs. And the difference of the logs is the log of the ratio. So 1 plus m divided by 1 minus m, right? That has to equal 0. And how else can I simplify? I could cross off the ends, cancel the ends. So then what? I get that the log of 1 plus m over 1 minus m is 2h over kt, I guess. So 1 plus m over 1 minus m is the exponential of 2h over kt. Since you remember that whenever I write log, I always mean natural log. Right? So it's like that. And now this is an equation which is not too hard to solve for m. Let's see. That makes a 1 plus m is equal to e to the 2h over kt minus e to the 2h over kt all times m. Okay, so if I get all the m's on one side, m times 1 plus this thing, e to the 2h over kt is equal to, oh, what is this? E to the 2h over kt minus 1. So m is equal to e to the 2h over kt minus 1 divided by e to the 2h over kt plus 1. Okay. And let's see, to make this look nicer, I can multiply both the numerator and the denominator by e to the negative h over kt. So if I do that, this is e to the h over kt minus e to the negative h over kt divided by e to the h over kt plus e to the negative h over kt. And this is a function which you might or might not recognize as a hyperbolic function, right? So in particular, this is what is called the hyperbolic tangent function, and the abbreviation for that is TANH, and Americans say that as tang, something like that. Okay, so it's the family of functions like sinh and cosh for the hyperbolic sine, the hyperbolic cosine. So we then would say this is just equal to the hyperbolic tangent of h over kt, like that. So here's our answer, okay? And it's an answer which we could have gotten from a much easier method. Some of you might have seen an easier method in previous classes for calculating this as an expectation value of the magnetization.
Question.
But I like this method. And the reason that I like this method is that it goes along with a picture of minimizing a free energy, right? That we had the free energy plot that I showed you in Mathematica a little while ago. And this is showing, you know, we search for the minimum. And here's the minimum of that free energy plot. Right? And it's something which responds to the applied magnetic field. Now, we might want to know, what does this look like if we make a plot of it? Okay, so I can do that on the computer in just a moment, but before doing it on the computer, let's just see what we can tell just by looking at it, because that's good practice, right? So you might or might not be familiar with this hyperbolic tangent notation, but you know, you can always go back to this kind of thing and say, what do you get for different limiting cases? Okay, so for example, suppose we have h equals 0. Okay. Well, if we have h equals 0, then the numerator here is e to the 0 minus e to the 0. That's 0. Okay. The denominator is e to the 0 plus e to the 0. That's 2. Okay, so it's 0 over 2, right? So the function is 0 there. So h equals 0 requires m equals 0. And you already knew that from looking at the graphs, right? You knew that when we had 0 applied magnetic field, that the function was perfectly symmetrical, right? With a minimum right at 0. Right? So this goes along with that. What about if h is really big? Okay, so let's say if h goes to positive infinity. Right? Well, if h goes to positive infinity, then in the numerator, we have a really huge number here minus a really tiny number there. Okay, so forget about the tiny number, we just have the huge thing. Okay? Similarly, in the denominator, we have a huge number plus a tiny little number. So yeah, forget about that thing. Okay? And so in that limit, m is just this exponential divided by this exponential, right? So it's just 1, right? It's a ratio of something divided by the same thing. So when h goes to infinity, m is positive 1. Okay. What about if h goes to negative infinity? If h is negative infinity, then it's the same argument as I had last time, but just turned around, right? And so now this thing is tiny, right? When h is negative infinity. But this is huge. Okay? Likewise, in the denominator, this is tiny, but this is huge. Okay? So we have, if we forget about the tiny things, we have a negative huge thing divided by positive same huge thing, okay? And that's just negative 1. Okay? So m is negative 1. So if I were to make a plot of this function, let's see, I could make a plot of m versus h. And I would know that when h is 0, m is 0. And when h is really big, m has to be plus 1. And when h is really small, m has to be negative 1. Okay. So in between, we have to connect up these points. Okay? And so then the question is, how do we connect them up? Right? And it might be that they connect up in a really sort of smooth way, like that. Right? Or it might be that they connect up, I'll do a different color, it might be that they connect up in a really kind of sharp way. Something like that, okay? So that the magnetic order is almost always plus or minus 1, except in some narrow little range, right? Or it might be an intermediate case between those things. Okay. And so what controls the sharpness is the temperature. Okay. So if we have a plot like this, well, a function like this, right? You could see, in this function, everything depends on the ratio of h divided by temperature and divided by Boltzmann's constant. So that means that if we have h equals kT, then m is equal to the hyperbolic tangent of 1, which is a number. I can't remember what number it is, but I'll look on my iPhone calculator app. I should have planned this in advance. Okay. Look, the iPhone calculator app knows about hyperbolic tangents, right? It's just right there in the corner. Okay. So if you do 0.1, no, not 0.1, 1. If you do 1 hyperbolic tangent, this is 0.76. Okay, so if I want, to say when is m equal to 0.76, that is when h is equal to kt. So, and likewise, when h is negative kt, here we have m is negative 0.76. If we were to change the temperature and repeat the experiment, right, we could say, at a high temperature, we need a really big magnetic field in order to get the 0.76 order. Okay, so this black plot is high temperature. Okay. If we were at a really low temperature, then even a tiny little field would give the 0.76 response. Okay, so let's see, that could be in blue. I'll mark this blue. That's not blue. Blue. This blue is low temperature. And the green is some medium temperature. So temperature is important here for saying what's the sensitivity to an applied magnetic field, right? At low temperature, it's really sensitive to a small magnetic field. At high temperature, not so sensitive, right? It takes a big magnetic field to get a big response. One way we might characterize that is by a quantity called the susceptibility. Susceptibility. That means if you are at zero field, so you start there, and you put on a little field, how big a magnetization do you get? Okay, so that means what's the first derivative of the plot at h equals 0? So the susceptibility, that's given the Greek letter chi. And so that is the derivative of m with respect to h evaluated at h equals 0, right? So you calculate the derivative and then plug in h equals 0. And you can do that if you either happen to remember the derivative of the hyperbolic functions, right? Or if you don't know the derivatives of hyperbolic functions, you could do it starting with that, but it's a little bit of work to apply the chain rule multiple times. But anyway, I'll just tell you the answer. Whoops, wrong pen. That the answer is equal to 1 over kT, right? So the high temperature, low susceptibility. Low temperature, high susceptibility. Okay, so this is my story about the non-interacting Ising model. okay? And I have computer-generated plots in the Mathematica file and in my book, so you can look at nicer looking plots in addition to these ones that I just made by pen. Okay. Any questions about this non-interacting system before I go on to put in interactions?
Yes, I have a question.
Please, Jen.
I think you are calculating the most probable and not the expectation value of M, right? Here in this.
They come to the same thing.
In the thermodynamic
in the thermodynamic limits, that's right. So there are fine distinctions for a finite system. And I'm not going to go into those things now. But yes, you are right that I'm calculating a most probable value rather than an expectation value, but it comes to the same thing in a limit of an infinite system, which is the limit that I care about here.
Okay, thanks.
Great. Okay then. So now let's go back to our original idea for the Ising model and put the interactions back in. Okay, so you remember that for the Ising model, we are assuming an energy which looks like this, right? The negative constant times the sum over nearest neighbor pairs, sigma I, sigma j, and then minus h times the sum over all the spins of sigma I. And in the calculation that I showed you so far, I considered only this part and I neglected that part, okay, the interaction part. Now, I want to put the interaction part back in. Okay. And that makes a harder problem. Right? In fact, it makes it a vastly harder problem, not just a slightly harder problem. And you know, the reason why it's much harder is that now we can't do calculations separately for each spin and talk about the probabilities for each spin. Instead, we have the interaction between neighbors that's included in a term like this one, okay? So, for example, suppose we wanted to figure out the free energy, okay? If we want to do the free energy, we would say, the free energy. So that's the energy minus temperature times entropy. Okay. We know how to calculate the entropy, right, in terms of the magnetic moment, or the order parameter M. Right? We know how to calculate this term in the energy, but how do we calculate this term? It's not something that just depends on M by itself, because it includes, you know, what's happening between neighbors, and we need to know about correlations between neighbors. Okay, so you know, even if we wanted to know the average of this, it's a little bit tricky, okay? So if we want to know the average of the energy, okay, that would be minus j times this sum over nearest neighbor pairs of the average of sigma I, sigma j. And then minus h, sum of the average of sigma I. This thing is easy, right? That is just this magnetic order parameter m, as we've been talking about. But what is that thing, right? It's not at all obvious how that should be related to m. Because this is not an exactly solvable problem, I have to make an approximation. And so let me tell you about a type of approximation that is widely used in this sort of situation. It's an approximation called mean field theory. And the basic notion here is that we will just neglect the correlations between spins. So we're going to treat each spin as if it were some independently fluctuating object with a statistical average of m, and throw out all the correlations between them. Okay? So we'll treat the spins, as if they fluctuate independently. Okay. So that means that when we get to an object like sigma I, sigma j, and we want the average of that, we will approximate that as if it's just the product, the average of sigma I times the average of sigma j. Now, if you were ever taking a statistics course, right, and you write something like that, okay, your teacher would say, no, that's wrong. You can't do that, right? And your teacher would be correct. That is wrong, right? This is not a general principle. This is some approximation. And, at this level, I can't tell you for sure if it's a good approximation or a bad approximation, okay? But it is some approximation which will allow us then to move forward, okay? So let's move forward with this approximation and see where it takes us. Okay, and I'm going to show you that it actually takes us someplace kind of interesting. So we're going to now use this approximation to work on the free energy. Okay. So the free energy with that approximation, okay, that's going to be this negative j, and we have the sum of all the nearest neighbor pairs of the average of sigma I times the average sigma j. So two factors of this average. And then minus h times the sum over all the spins, the average of sigma, and then minus ts. Here, this we already talked about. This is just M. Okay. Now, with the enormous approximation that I'm making, this thing is also just M. Okay. That's at site number I. This at site number J, well, it's still the same because there's no difference between one site and another site. So it's just another factor of M. So the product of those things is just M squared. Now, we have to say, here we have a sum of a bunch of terms, okay? And all these terms in the sum are exactly the same. So we just have to multiply by the number of terms in the sum. Here, the number of terms in the sum is just n terms, right? If for n sites. Here, this is a sum over all the nearest neighbor pairs. Okay, so that means if we have a lattice, like, oh, here's a bunch of sites in a lattice. Okay, and now I want all the pairs, like this pair, this pair, this pair, right? And so let's see, how can I count how many pairs there are? Well, for one thing, I could say there are n sites, okay? So if there are n sites, and then we can say, well, for each of the sites, how many neighbors does it have? Well, in this case, each site has 4 neighbors, right? 1, 2, 3, 4. If it were a different kind of lattice, it would have a different number of neighbors, right? So, for example, if it were a cubic lattice in 3 dimensions, then each site would have 6 neighbors, right? It would be these 4, east, west, north, south, plus up and down. Okay, so 6 in all, right? So the general word for that is the coordination number, okay? So the coordination number is the number of neighbors per site. That gets the letter Q, lowercase q. Okay, so in this example, we have Q equals 4. All right, so then if we want to say, you know, how many nearest neighbor pairs are there? In the whole lattice? Well, you know, your first naive guess would be maybe it's n times q, right? If there are n sites and each site has q neighbors, actually that's slightly double counting because we would say, you know, if we look at this pair, well, we could say this guy is a neighbor of this guy, right? But we could also go backwards and say this guy is a neighbor of that guy. And so if we do the NQ, that would be double counting, exactly a factor of 2. So to compensate for that, we should really multiply by 1/2. Okay. So there are 1/2 NQ nearest neighbor pairs in the whole system. Okay. So that then goes into the free energy. Right? So in the free energy here, we have this sum over nearest neighbor pairs, and every term in the sum is the same m squared. So we have 1/2 NQ such terms. So the, whoops, wrong pen. So the free energy is -J times 1/2 NQ pairs, and each of those gives a contribution of m squared. Okay. Then we have the other term in the energy, the term that we already know about, the -HNM. Then we have the entropic piece in the free energy. That is this subtracting off temperature times entropy, and the entropy depends on m in the way that we already figured out in the last class. Okay. So that turns into the same thing we had in the last class. So KTN 1 plus m over 2 log 1 plus m over 2 plus 1 minus m over 2 log 1 minus m over 2. All right, so this whole thing then is the free energy of the Ising model with interactions in the mean field approximation. Okay, so this is not exact, but this is the mean field approximation.
Dr. Selinger?
Please.
How much more complicated would this problem have been had you not made the mean field approximation?
1,000,000 times more complicated.
Okay,
I mean,
I was just
curious. I don't know. I mean, it would have been vastly more complicated.
Okay.
And in general, it is not solvable exactly based on decades of research. There is an exact solution for the specific case of a 2D square lattice, but that's kind of a unique, one-of-a-kind solution, and there is not a solution in general for other dimensions or other types of lattices. Now, there has been quite a lot of research on doing better than mean field theory, and I'll get to some of the comparison coming up in a little bit.
Okay, thank you.
Good. Now, this equation, though, I mean, even with the approximation, is, well, I mean, it might look a little bit confusing. So let's try to interpret it, okay? So first, I already looked at examples where there's an H but no J, okay? Now, how about some examples where there's a J but no H, okay? So let's do that, okay? So I'm gonna temporarily not think about H, okay? And so let's say we want to make a plot for f as a function of m for h equals 0. Okay. But I will have a non-zero, specifically a positive value of j. Okay. And in particular, just to make the plotting simpler, I'm going to divide this by nkt. Okay, so that means I cross off that factor and I cross off the n there, and I'll put a kt in the denominator. All right, let me go back to Mathematica for that. All right, so I'm going to turn off my whiteboard and turn on the Mathematica. How do I do that? Stop share, all right, and then share Mathematica. Okay, you guys see that? Good. All right, so here we have a plot of this combination. Okay, so the second part of what I'm plotting, this is the entropy, as we saw before, divided by nkt. The first part of what I'm plotting is now this mean field approximation for the interaction energy. Okay? And I have cleverly chosen my variable name, jq over kt, and that means J times Q divided by Boltzmann's constant divided by temperature. Okay. So here is a plot, and I'm going to now adjust the slider to vary this quantity JQ divided by KT. Okay. So when this is 0, the plot is like what you've already seen, right? That is, it looks like a parabola. And it's easy to know where the minimum is. The minimum is right there at m equals 0. Now, suppose I gradually crank up this parameter JQ over KT, okay? So in an experiment, you could either imagine you're making the interaction stronger or you're making the temperature lower. The second thing is much easier to do than the first thing in an experiment, okay? So suppose you have a sample with fixed interaction strength, J, and fixed coordination number, Q, but you're gradually reducing the temperature. Now, as I reduce it, you can see the plot is getting kind of flatter. So there's still a minimum right there, but it's not so steep, right? It's a really kind of flat plot. Now, as I continue, it gets really flat. It doesn't look so much like a parabola anymore. It looks more like a quartic function instead of a quadratic function. Now, look at what happens when I keep going. Now the plot kind of turns over in the middle, okay? So that instead of having a minimum right here, it now has a local maximum right there. So where's the minimum? It shifts outwards, okay? There's one minimum there, and there's another minimum there. That means that the magnetic order parameter is not going to be 0 anymore. It will either be this value, about positive 0.5, or it'll be this value of negative 0.5. Which will it be? I don't know. It could go either way. It's random. It will randomly go in a positive magnetization or a negative magnetization. Right? That means that as you reduce the temperature, okay, you have a system that has no magnetic order, no magnetic order, no magnetic order. And then when you hit a certain temperature, you say, ooh, there's a little bit of magnetic order, right? The minimum is a little bit off from zero. And then if you continue to reduce the temperature, you get more magnetic order. And if you keep reducing it, it gets farther and farther out. The minimum just keeps shifting out towards perfect magnetic order. This is a phenomenon that goes by the name of spontaneous symmetry breaking. Okay, so that means that at high temperature, there's a symmetry between spin up and spin down, right? You remember the positive M means spins are mostly up. Negative M means the spins are mostly down, okay? At high temperature, the spins are mostly zero, right? Half are pointing up, half are pointing down, okay? If you reduce the temperature, you'll stay at that symmetric state, half pointing up, half pointing down, until you get to a certain specific temperature, which is called the critical temperature. Okay? So at temperatures above Tc, there will be no magnetic order. Okay, so if T is greater than Tc, there will be no magnetic order, that is, M equals 0. But if T is less than Tc, there will be magnetic order. That is to say, M is not 0, okay? And it will be random which way it goes. It will be randomly M is positive or M is negative. So this is the concept of spontaneous symmetry breaking, right? That all by itself, the magnet randomly will point mostly up or mostly down, okay? It could go either way. The word spontaneous means that there's no external influence that makes it go one way or the other. Okay, so it's different from the case that I showed you before, where a magnetic field makes the order go one way or the other. Here, there is zero magnetic field. So all by itself, the system randomly goes one way or the other. This is a really general phenomenon in statistical mechanics, right? There are lots of important systems where there is order that randomly goes one way or another. Another example that we're going to be leading up to in this semester is a liquid crystal, right? A liquid crystal is a system where when you cool down, the molecules randomly pick some direction to align. Could be randomly this way or this way or this way or anyway. Okay, so this is my first mini example, kind of a simple example of this phenomenon of spontaneous symmetry breaking, right? Of the formation of order in some random direction at a certain critical temperature. Okay, now I see I've gone a little bit over time because I get so excited about this stuff. So I am going to stop talking here. I can answer questions or I can let you guys go for now. And Dan, I see you're here. Please stick around afterwards to talk for a minute. Okay, you know that Monday is a holiday, right? And so today is Friday. Monday is the US holiday of Labor Day. So that is a day in honor of American workers. This is the holiday that most countries have on May 1st, but in the US we have it in September. So you get the day off on Monday so you can think about American workers, and I'll see you guys on Wednesday. Thanks.